Speeding, action.
Hi, I'm Arnold Schwarzenegger. That's right, Arnold Schwarzenegger. You're probably wondering, where's my thick Austrian accent? Gone. Thanks to Axagon, the accent eliminating spray. It's terminated. One thing you need to know.
Arnold? Can we go again?
I thought that was good.
Yeah, it was great, but your accent creeped in a little bit, and we can't have any.
Really?
Yeah, just
Axagon, the accent eliminating spray. It's terminated. It works naturally in
Arnold, can we just start from the top?
Why is that? Thanks to a revolutionary all-natural throat spray, it works fast, effective.
Arnold, it happened again.
Yeah?
Yeah. So let's just start again. Okay, and
I don't know what you're hearing.
And action.
A revolutionary new throat spray called Axagon will completely eliminate your accent, guaranteed.
Okay, cut.
Really? After just 2 weeks of use, Axagon will completely eliminate...
Arnold?
What? Axagon is a throat... I can do this. Let's start over. Check out some of these lines accent-free. It's not a tumor. Get in the chopper. Cohagen, give them their air. Who is your daddy? And what does he do? Who is your daddy? Who is your daddy? And what does he do? Well, I hope you left enough room for my fist, because I'm gonna ram it into your stomach and rip out your goddamn spine. That's good, right? With Axagon, I guarantee your accent will never say, I'll be back. I'll be back. Never say, I'll be back. I'll be back. I'll be back. Yeah. Your accent will never say. I personally...
Are you alright on
Yeah, you know what? Let's go with this.
All right,
Let's
ready?
I'm ready.
All right, we are rolling and action.
Well, I am a governor of California. I'll be back. Axagon. Available at finer pharmacies everywhere. This.
Good afternoon, folks. It is your old pal Dr. K, giving you some science on this overcast afternoon here, and thanks to our president who gave us the day off. Essentially, we can have this time to learn about some science. Right? Let's do this. What are we doing? Grignard addition or so to these nitriles. So we're going to take something that looks like this Grignard addition here, this Grignard reagent, and add it to this nitrile looking thing to overall, after hydrolysis, will give us a ketonic species here. And let's do that out sort of in gory detail. We won't probably use those exact ones, but we'll use something very similar to it. So let's just switch to a nicer background here. We can, oh, look at that personalized background. Fancy schmancy, no? All right, let's talk about, let's do something fairly simplish here. Let's take, all right, let's just, you know what? I gotta draw. Now we're good. All right. Take something that looks like, we'll just say that. Uh-oh, we have issues. This is my, okay. Can I zoom out? Zoom out. I can't zoom out. That's not happening. Stop it. All right, let's try this again. How wonderful technology is. Or how wonderful having a very, very old person trying to use very, very complicated pieces of equipment. All right. Let's take this, try this again. Boop, boop, boop. And we will just use, you know, nitrogen there. Okay, we will just use isopropyl Grignard. MGBR. All right, we'll take that guy there, and then we see what happens. So this is the first step there. Our second step will be acid hydrolysis. So just H plus, and we're going to assume that we all remember that that's also in water too. And when that happens, right, what we do is that to find out what we have at the very end, so the end product, we're not even doing the mechanism, we can just sort of see, we can just sort of imagine that if we have one we have 1, 2, 3 carbons. All right. Then the carbon of the nitrile will be the carbon of the ketone. And then the rest of it will be the Grignard adduct. So that will be our overall product, all right? That'd be our overall product. So how do we get to it? Let's see if we can get to it fairly easily, all right? It's not that bad. The first part is dead simple. The other part there, we've talked about the mechanism before. It's just a little tedious, but it's you'll see, it's not that bad, all right? And I might have to wipe the screen just once to get some more room. Okay, so we'll just start. Okay, so here's our cyano. Here is our nitrile species. Here's our isopropyl species here, and I'm just going to draw out the MgBr. All right, and this guy here is going to attack into that cyano group right there. You're going to kick up that pi pair of electrons from that triple bond into the nitrogen atom itself. All right, so our adduct here overall is going to be, and here's going to be our carbon of addition here. Here's going to be our double bond. Here's going to be our nitrogen. Now remember that nitrogen already had a lone pair on it to begin with, so now it has 1, 2, 3, 4 lone electrons or 2 electron pairs there, and then your adduct is going to be that. Now you see how this almost looks like the product? Oh, we forgot this. Boop. Right? See how this guy here looks like, this intermediate looks like our final product almost, right? Now, so we've done essentially our first step. We've already done step 1. Now step 2 is all that's left. We would do the acid hydrolysis, right? Which is going to be very straightforward. All right, so now we're going to do step 2, and then let's just throw in some acid, right? And we're going to use H plus and H2O as needed. So first we'll use our H plus. Have this guy here grab H plus, of course. And again, this is going to be the tedious part that you've already seen a few times with a few similar mechanisms. You know, the amine mechanism, the hydrazine to hydrazone mechanism. You've seen that in a very similar fashion. So there is this is a nitrogen, by the way, here, right? Nitrogen, by the way, here, right? And so then what's left now? So now we have this neutral species right here, but then remember, we still have more H plus. We have as much H plus and as much water as we need. All right, so let's just grab another proton from some more H plus that's been floating around. All right, let's just draw that again. And again, I'm gonna have to probably wipe the screen because I want to make sure we have enough room here. There's our net. Wow, this is bad in terms of like drawing, but I'm trying to draw this thing on a tablet, and it's just I can't. It's weird. If it's not a fountain pen from the 1940s, I'm sort of lost. Even then, right? Okay, nitrogen there. Wow, looks like a maniac from an asylum is drawing this on. Now, again, not that far off, right? But so there's a plus charge there. All right. Ugh, let's just wipe the screen. Let's just start at this guy here on the next screen. Okay, let me just erase this part there. All right. Boop. All right, here we go again. Start off from that protonated nitrogen species. All right, this is a key step here. Okay, so we just got from that carbon double bond nitrogen with the hydrogen on it there, and then we just grabbed another proton from the end of that last screen, right? Now the next thing here we have to do that's very important is grab, right, that electrophilic character from that carbon, right? So again, because we have H plus and water in there, we're gonna have that water here attack in to that carbon right there, and this will swing on up. Why will that happen? Well, this oxygen here is partial negative. This carbon here is a partial positive. Well, you say, well, if this is a partial negative, don't you want this guy here to go towards the most positive thing? Yes, but think of it here. If this oxygen attacks that nitrogen, what good does it do? There's no positive effect that it has. Like you can't make a stable species, this ON species there. But but what you can get after you have this oxygen attack this carbon is this pair of electrons swing up to that nitrogen that quenches that positive charge right there. So that's an overall positive effect, right? And so that's what we want to do. So I'm going to draw this water here. So I'm going to draw this nitrogen here. I'm going to do a shorthand NH2 there, and I'm going to draw this OH2. I'm not going to forget our positive charge right there. Okay, so we're almost to the final step here, right? All right. So now what we can do now is we can do normally, if you guys feel comfortable at this point here, you can do a proton transfer, and that's what I would sort of recommend you doing. Right, just do a tilde H plus, right? And I would just proton transfer a proton from this hydronium species, this oxonium species, to this nitrogen species over here, right? Or if you want to, you can have water come in, pull off a proton there, then have acid add a proton to this nitrogen here, because overall, at the end of the day, you want to have this carbon-oxygen bond here be the functionality here. You want to have this guy here leave. You have no amine species in your final product, okay? But for the cool kids in the audience, if you guys want to do the proton transfer to go from there to there, that's totally fine with me, right? And just do the little tilde H plus. There's no need to draw any arrows anywhere. I'm trying to remember to keep the carbon there, right? All right, so now we have NH3 plus. Now we have a great leaving group, right? And keep that there like so, and keep this here just like that. Okay, notice that going from this species here to this species here, we did not change the net charge on the species. It's still a plus charge. It's still a 1 plus charge here, and it's still a 1 plus charge here, because the plus charge here, right, corresponds to the oxygen. The plus charge here corresponds to the nitrogen. All right, and so what we can have happen now is we can have a few different things happen. You can do this in one step or a few different steps here, but I'll just do it this way. I'm going to have one of these lone pairs here swing on down in between that oxygen and carbon bond here, forming a carbon-oxygen double bond, through the pi system. And when that happens, that kicks off this very good leaving group now, because this nitrogen here does not want to be positive. It wants to at least be negative. So when we do that, what we end up with is this charged species here still, right? Plus, and a plus ammonia here essentially, right? And you have that species right there. Right? And so now you are very close to your final product, right? You are very close to your final product. You have, your final product looks like this ketone species, except it doesn't have the proton on it, okay? So your choice. You can have ammonia come in and pull off that proton because it's local to it here. Or if you want to, you can have water come in and pull off that proton, whichever way you want to do. Because because there's so much more water in that, oh, stop it. Okay, I guess we're zooming in. Because there's so much more water on that species here, what I'm going to do here is I'm just going to have water in the close-up. I'm ready for my close-up. All right, there's this. Have water come in here and yank off that proton right there in close-up. And it's going to swing on there like so, and it's going to give you your final overall product. And your product here is going to be what you imagine it's going to be. That, okay, plus your H3O plus, which is your H plus and H2O. So there is how you can go from your nitrile species to your nitrile species and a Grignard to your ketone species, right? So that's pretty cool, isn't it? Okay, and that you see that very last those last steps here are very they're very tedious, but I think you've seen them before in a few different respects. All right, so there's that. Let's get back to our regularly scheduled program. All right. Okay. So that's a cool little diversion that we had, right? Just being able to talk about how to convert these nitriles and ketone species into ketones overall, right? So that's another functionality that you have, in addition to all your other functionalities, like like oxidation, like ozanolysis, and so forth and so on. Now you have another thing to be able to access ketone species, right? So just a synthesis of this top species here. See if I can draw on here without screwing it up too much. All right. Draw this guy here, make this guy here from this species here and this species here, right? And we won't go over it. It's pretty straightforward. Like it's very similar to our previous mechanism, but there is a key thing that you have to see here, right? It's not about the chemistry that we just talked about. It is about the strategy that this specific problem is asking you to use. Notice how many total carbons you have in the side chain. You have 1, 2, 3, 4, and 5, right, in that side chain. So that side chain is going to come obviously from this species right over here. But notice you have 5 carbons here, but you only have 4 carbons here, right? And so when these carbons here, and also in this benzene here, this bromobenzene here, you have a bromine here, not a carbon species, all right? So now you have to ask yourself a few different questions, right? First off, okay, well, how do I add a carbon between this species here and your benzene species here? Well, do I know how to do that? You do. You do sort of here, but can you do it here? Can you do it at the benzene? I'm pointing here because I don't know if you can see the cursor or not. Can you do this here at the benzene? You don't know how to add a cyano to a benzene just yet. You might soon at a certain point, but not right now. So right now, use your own sort of like ignorance of this chemistry to your advantage. Like, well, I don't know this because he didn't teach it to me and it's not in the book, so I don't know how to do it yet. But I do know how to add a nitrile to that species right there. And how do you do that? Of course, you know how to do that, right? That's pretty simple, right? That's just see if I can erase here. Right? How do you add to this here? Well, how do you make the cyano here? Well, convert to some leaving group here. Maybe, I don't know, make this into a bromine as well. Br and 1, 2, 3, and 4. You know how to do that, right? Or chloro, or whatever, or tosyl. And then how do you add a cyano to this guy here, right? How do you add a cyano to this guy here? I think you already know, right? So I want to make this into here we go with the zooming in. I really can't control, I can control it, I just don't know how I'm doing it. If I wanted to do it, you bet your ass I couldn't do it. But I don't know how I'm zooming in. So let's just enjoy the zooming in because it's a special effect. And because we all love special effects. Sorry, I'm lashing out at technology because I'm an old, confused man. That's why. How many carbon? 1, 2, 3. So 1, 2, 3, 4. And this guy here, right? So we have to add in. So here's a cyano here. That's going to be the carbon that goes right there. And you have 1, 2, 3, 4, right? So then we have the rest of it's going to be 1, 2, 3, 4. 1, 2, 3, 4, 5, right? Is that gonna work out right? Do I have enough carbons there? Is that going to work out? Let me just see. Is that going to work out? And let me just zoom out again here. I don't know. I have to erase it or I have to zoom out. Hold on. No, yeah. I have plenty of carbons. So I have 4 carbons here. So I want to go from there, right? I'll go from there, and I'll just, again, from there, again, make this into a leaving group, so like a bromo or a chloro, then convert that into a cyano group here. 1, 2, 3. 1, 2, 3, 4, right? And how do I go from the bromo species into the cyano species here? That's a pretty straightforward transformation. It might be, you might want to use your plain old chapter, chapter 5 or 6 or whatever. Plain old semester 1 SN2 chemistry. Very straightforward stuff. Then once you have this cyano right here, right? Once you have that guy here, then I think you know how to go from this guy here to a species that would give you the ketone there. Make this guy here into a Grignard. So treat that guy here with some magnesium turnings in dry ether. And then we're going to zoom in on the ether because we're going to interview it apparently. All right, because it was part of the Monica Lewinsky affair or something to that effect. All right, so yeah, make this into a Grignard somehow. Okay. And once you treat that Grignard with that cyano species there, then you have your overall then you have your overall species there that you want. You want to treat that with, you want to react that Grignard with that cyano group there, then follow it up with the acid water workup, just like in the previous slide. And I think that you'll see that you'll get the product that you want. All right. Cool. All right. Let's see what happens next. Okay. All right, and so we talked a little bit about additions to the carbon-oxygen double bond before. We've done a lot of this when we talked about the Berge-Dunitz trajectory. We talked a little bit about that last few chapters ago too, and also we've been adding stuff to ketones all the time. We've been adding Grignards essentially to ketones and to make alcohols. We've been adding hydrides to ketones to make alcohols after hydrolysis, right? But you can add more stuff to them, and some of that stuff is really helpful, thankfully. All right. And so what we're going to do here is, and as you can see here, that these groups, these angles here are sort of approximates, right? These aren't really 120. These are approximate 120s here, but that's going to be good enough for government work for us. We're not going to care that much about the differences of angles. It's just going to be roughly 120 degrees between all those angles here, and that's all we need to know to worry about. But it is sp2 hybridized that carbon, and it is a trigonal planar structure. All right. All right. So let's hit on down to this other slide. All right. So just based on your ideas of resonance and induction, that carbonyl species here have a sort of a dipolar idea about them, right? You have when you have your carbon, your carbon here is a partial positive charge, your oxygen here is a partial negative charge, right? And the reason why they have these charges here is because through resonance they can become a full negative charge or a full positive charge. And essentially this guy here is essentially its own resonance hybrid picture of what this would look like, right? Of what this other resonance canonical form would actually look like too. And so one of the things let's just make a fine point on it now, right? That oxygen right there is going to be a nucleophilic species when we need it to be. And I think we've already used that as a nucleophilic species. Remember when we've taken a ketone and we've treated the ketone with a Grignard reagent, we have an O- charge. And that O- charge from the resulting attack of that Grignard, we can either quench it with a water or with an acid, or we can have this thing attack a alkyl halide to give us an ether. So we have a lot of different functionalities there. This carbon here, which with the positive charge right there, is a species that can accept some electron density. It is something that can take on, of course, a Grignard, but also even less strong than a Grignard too, like some alcoholic species or some aqueous species. Okay, but those are the different variables. Those are the variations of things that can attack a ketone species, or a ketone species can attack. All right, and note, a nucleophiles usually do not attack a non-polarized carbon-carbon bond. That's the difference between a carbon-oxygen bond and I'm just going to draw this carbon. This might seem like sort of like a really obvious, comparison, but it's worth mentioning. It's a good point, right? The reason why we have so much reactivity between a ketone, a carbonyl, is because of this very polarity. The reason why you don't have that kind of reactivity with an alkene or an olefin is because you have no such differences, no real differences anyway, in polarity between that carbon there and this carbon there. You don't have too much difference, so it's not going to be there's no dipolar reactivity, right? That's a sort of important thing to do. But just for funsies, let us attack a ketone here with a strong and a weak nucleophile to see what happens. Again, it's going to be like not very exciting, but it's still something that we need to know. We need to look at. All right, and so let's just take plain old acetone here, and we'll use a weak nucleophile, right? And the nucleophile that we'll use here will be methanol, right? Methanol. Yeah, what the hell? We'll use methanol, right? H3C, OH. Take this guy here, attack in just like so. Kicks up like that. Why is that oxygen attack that carbonyl? See the previous, 10 minutes of like going over why this is a dipolar species. All right. So now we're just going to draw in the. Did you hear that evil voice in the background? Yeah, that is a baby toy that we haven't put away yet, and my children are not that young, and they haven't played with that toy in a long time. I'm just behind in putting crap away, right? Sometimes I'm reminded that Y is for yarn. Okay, there's that. Okay, so there is that species. This is that highly charged species there, which is not so stable as in that form. So what we're going to do is that we will just take that species there and we will do a proton transfer. Tilde H plus. That's a plus, believe it or not. Not some sort of a weird European money sign or whatever. All right, so what are we doing here? So the proton transfer from this hydronium species to that oxide species. So what we end up with is this guy over here. Over here, right? And so and that happens, and this definitely does happen. And not only that, but we're missing one very important little feature about this. This is actually, as you can see here, even though it seems like it's a nucleophilic reaction, and it is, it's also classified though under an acid-base reaction, because this guy here, right, this guy here as acting like a Lewis acid, this guy here is acting like a Lewis base. A Lewis acid can accept electron pairs. This and the Lewis base can donate electron pairs, right? So this is an acid-base reaction, so you can really do this equilibrium arrows, and that would be the most correct way to draw this reaction. It is definitely in like equilibrium, so there's that. So this is a weak nucleophile. This is a weak. And why is it a weak nucleophile? See, it looks like work, like as in torque. It's weak. Oh, that's way clearer. All right. Why is it weak? Because this guy here is non-charged. It's not like it's a strong. It's not a strong base, which in certain ways parallels strong nucleophiles too. But also there's we talked a lot about strong nucleophiles versus weak nucleophiles last semester. So please refer back to your old notes there to talk about for those discussions. Let's use a version of this as the strong nucleophile and just see how much simpler that actually is. Because with a weak nucleophile like this one specifically, you got to deal with, after the initial attack, you have this tetrahedral species here. You have to also sort of neutralize this, bring it down to a place where you don't have a lot of these internal charges to lower the overall energy of the species, right? And so that's something that you have to worry about, because like we talked about before, when you begin with neutrality, you have to end with neutrality, and that's what you're doing. But let's see if that same sort of adage holds with the strong nucleophile. All right, let's say CH3 carbon O minus. Let's just use methoxide versus methanol. Let's use like sodium methoxide or potassium methoxide. I won't draw out the other potassium or sodium, as it'll just give me more opportunity to be messy. All right. And so again, you can do the same exact, very straightforward sort of nucleophilic attack of that guy there to that guy right there. All right, and there's that. O minus there, and then oxygen there. CH3. Okay, here's your minus charge there. All right. So, and we're done with that. This is going to be the strong. Wow. Thank you, One Cob tablet. This is terrible. All right, strong, believe it or not. All right, this is where it ends, right? Because this alkoxide, this methoxide here, attacks into that ketone species there, and that's all. That there's no There's no protons to transfer. There's no nothing to transfer. I mean, if you wanted to, okay, let's be nice. If you had a potassium here, after you attack that here, the potassium would be there, but there's no like potassium transfer mechanism. It's just the potassium hangs out wherever the negativity is. It's a sucker for some negativity, right? And so it wants to just hang out at whatever's charged, so it can help neutralize it. But notice that you have a charged species here, and you can have a charged species. You have a charged species here for your reactants. You can have a charged species here for your products. Just like this guy here up here can be a neutral set of species for your reactants and a neutral set of species for your products. The same thing goes the same way for charged versus charged. Okay, so this is a weak nucleophile here versus a strong nucleophile addition to ketonic or ketone species. Okay. All right, let's get back to the other thing. All right. Relative reactivity of aldehydes, ketones, and esters, right? And why are these things relative? Why are these things reactive or not? And there's a few different factors sort of going on simultaneously here. Why are the aldehydes more reactive than the ketones, and why are the ketones more reactive than the esters? Well, there's a few different things, and let's talk about one of them first, and then we'll talk about the other one that's maybe a little bit less important. But the first reason why, let's just say the aldehyde is more reactive than the ketone is because it's just plain old sterics. Let's say this R is not hydrogen. So even more reactive. Let's draw an even more reactive thing. Even more reactive is like the most reactive ketone species is formaldehyde. All right. Why? Because you have two hydrogens there. They're very small, and it'll let whatever goes, whatever wants to head in and attack that carbon, it'll just let it pass. But once you have an R group here, and the R group can be a methyl, it could be something that's not hydrogen, but it'll offer some sterics, and we'll just draw a little circle around that to show sterics. Whatever wants to come in from some direction has to sort of drive away around that R group here and then head into the ketone species here. So it's going to offer right about here some steric aggravation, right, to be able to get around it, to be able to attack into that ketone. So the reaction here is going to be a little bit slower than this guy here, than this other species here, which can just sort of head right in through the front doors and unchecked, essentially, right? So the bounce is not on that night. The bouncer who's a jerk that night is not on. You just walk right in, right? So then there's that, right? But now let's go from this aldehyde species here. So you have a formaldehyde, you have an aldehyde species, which is more reactive. And then you have and this guy here, which is even more reactive than this ketone right here. This ketone here now offers you lots and lots and lots of sterics, right? Lots and lots and lots of sterics here. This guy here is going to be even hard to get through. Let's just say this is the path of my nucleophile here. It has to just sort of squeeze in between these two bulkinesses here, these two sterics right there, to attack into that ketone. Oh, and now we're zooming in because that's the thing. All right. Oh, you know what? I'm not drinking. I'm drinking coffee right now, but I want to pause the thing and get booze. All right. Anyway, so at least I'm just throwing some anisette into this coffee, which sounds like a great idea. All right. So this guy here here's the path of the nucleophile here. We'll just kind of go in between those two R groups here, which could be methyls, it could be ethyls, it could be whatever, but it's going to offer some steric hindrance between those two guys here. And that's why this guy here, these ketones here this ketone here will be less reactive than the previous aldehyde. All right, I'll zoom on out. It's going to erase everything, of course. All right. And so I'll just redraw the formaldehyde here. Sorry about this technical thing, folks. I'm still trying to figure out this specific piece of software. All right. One day, 25 years from now, I'll be awesome at it. All right. So most reactive. So 1, 2, second most reactive. 3, third most reactive. This guy here, believe it or not, this guy here is the least reactive out of the entire 4. So this guy here is the least reactive. Why? It's actually not because of sterics. So if you have an R group here, This guy here was going to give you the sterics that you'd expect. But the R group here is actually way out here. So you'll actually have not as much aggravation due to sterics as you would even here. So this guy here is actually more sterically hindered than this ester. So this guy here has more sterics here, right, than this guy over here. So why is this the least reactive? Well, as you might notice here, this guy here has an oxygen here, and that oxygen here has a lone pair. And that lone pair can engage in some in some resonance here. There and there. Okay? And once you have that, now you have a situation where you have some resonance stabilization between between the lone pair of this oxygen here and this ketone right there, right? And then that resonance contributor, right, that canonical form will be this guy right here. And if you have some resonance here, this resonance here will offer some stabilization to this electrophilic carbon. And because it is now so stabilized through resonance, it will be less electrophilic because it has more stabilization of electron density around it, right? And just think about what happens if you do add something into this ester. Think about what does happen, okay? I'm going to erase this and then just draw out the hint for you. I'm going to erase this guy here. All right. What happens if I take this ester right here, just plain old regular, I'll just draw like ethyl acetate. And so now here I have resonance. Now I'm going to add in some species here that won't necessarily break it apart, but will do something to it. Let's just add in methanol. And I don't believe that methanol will really attack ethyl acetate. It's not strong enough to. But I'm drawing it as a theoretical so you could see what happens and why maybe it doesn't attack that ethyl acetate. Because look what happens. You know what? I'm going to do that, and then my second step, which I won't even draw, I'll just put a tilde H plus here to show you the proton transfer. All right. And what is here? Okay. All right. Here's my, so this CH3 here is that CH3 over here. That proton here, right, is from here after the proton transfer. Okay. So look at this species right here. It looks like it's relatively normal looking enough. Why? What's the big deal? Well, the big deal here is that it is a, what did it do? What did it do to this species? Look at this species here. Then look at this species here. What did this methanol do to this ester species here, right? What it did was it disrupted resonance. It took away the resonance stabilization, and it made this guy here into a sp3 hybridized carbon, which is, normally fine, except it's normally fine like here or there or whatever, but it's not fine here because this guy here already had some stabilization. It was already happy with its resonance. Once you take away resonance, you're taking away a lot of the source of its stability. And so you're actually going to be going up higher in energy, which is why methanol does not add. This reaction here does not happen. I had to show you that it did happen to show you why it wouldn't happen. This guy here, not stable because you took away. I don't like this new drawing program. I don't like it. It's too laggy. It took away resonance. I'm going to go back to the old drawing program. This took away resonance. All right, so that's why this is not a good thing to happen. So no, does not happen. All right, but you say you have added things before to ketones and especially esters, and there wasn't a problem there. You're right, but what did you add? You didn't add no measly methanol. You added, and ignore that other thing. You added, like, for example, you added like methyl grignard, for example. Like you added something with a strongly minus charge, some very strong nucleophile, methyl grignard, ethyl grignard, some grignard reagent, or some hydride. Even hydride's also fine too, because remember, look at the pKa's of either of these things here. These guys here are upwards of 40 and 50. Of course, these will add into there, because as much as this thing loves being stable, it can only fend off nucleophiles that are so strong. It'll fend off methanol, no problem, but it will not fend off, these Grignard reagents or these very strongly reducing reagents, right? So it can't defend itself against Grignards or like LAH or Dibal or lithium triterpenoxy aluminum hydride, but it can defend itself against methanol and weaker reducing agents like sodium borohydride, right? But not against lithium aluminum hydride, for example. Okay, is that cool? Is this all right? I'm gonna wait until you respond. Why am I gonna wait? I'm in front of a microphone. Why am I gonna? Okay. Anyway, so boop. Okay, so there's that. All right. So steric factors. All right, and we talked a little bit about this before, just on this previous slide here. The reason why this happens, this slide is showing you that if you have a nucleophile that is going to add into some sort of a ketonic species, you have to have something that is able to accommodate it here. So when you have aldehydes, you have one alkyl group followed, alongside a hydrogen. The hydrogen is roughly smallish, and it'll allow things to add into your ketone species. But if you have a ketone, a regular plain old ketone, you will have a harder time. Not that you can't do it, but you'll just have a harder time adding things into that carbonyl, because that nucleophile has to make it past those two R groups. Okay. The electronic factors here are less important, but still worth mentioning here. So if you have an aldehyde here, you have a positive inductive effect from the R group only. Okay, so so this guy here is will be positive here, because you have this carbon species here will be able to take on some more negative charges, because electronegativity is being pulled away from this carbon using this oxygen, and only this carbon here is really pushing any electron density towards it. So it's not going to be completely neutral. It'll have some positive charge here, especially because this hydrogen here is going to be so positive right next to it. But if you have this ketone over here, where you have two R groups right next to it here, you have positive inductive effects from both the R and the R prime groups. So the carbonyl here is overall less positive, because you have some electron density being dumped in by two R groups, one from there and one from there, right? So this is going to be overall positive, because the electron donation is going to be going towards this carbon from these two alkyl groups here, whereas in this aldehyde here, you only have electron density being pumped into it from this one alkyl group. I don't know if you can see any of my pointers. I'm going to draw this again. All right, draw. This guy here is pushing electron density into it here, right? Into this carbon that way. So it's dumping some electron density into it, making this guy here less partial positive than it might normally be. And this hydrogen here is not dumping really any electron density, right, into the carbon here at all. It's only, or maybe only a little bit, from its polarizable carbon hydrogen bond here. But as opposed to this species here, where you have a ketone, you have both these methyl groups, or both these alkyl groups, dumping electron density into that carbon species there, which is really removing a lot of this partial positive charge here, right? If these two guys here are equal, if they're both carbonyls, those have some effect on the carbon, but they're not. But they're going to be canceled out when you're comparing them next to each other, right? So that's not going to be an effect that you can really compare, because they both have the same thing for those two examples. But when you compare your aldehyde to your ketone here, right, you can say that your ketone here will be less reactive, because you have more electron density being pumped into your carbon from your two alkyl groups than you do on your aldehyde, where you only have one alkyl group dumping electron density into your carbonyl carbon. Okay, so there's your electronic factors. But if I had to sort of tell you what to stress on, I would just stress on the previous slide, about the previous slide's idea about sterics and what steric effects do to your reactivity of your ketones and stuff like that. Okay, so I'd more worry about this in the previous discussion there than the electronic factors. Okay. All right, and so now we have the additions to alcohols, for hemiacetals and acetals. Okay, and we'll just talk about this for a few more minutes, and then I will let you go, and we'll probably finish this up on whenever the hell I see you next. It'll probably be on Wednesday. Wednesday or Friday we'll finish up this whole chapter. Okay, but this is a really important mechanism here, and this is one of these mechanisms that just keeps on popping up over and over again. Okay, when you have some sort of a ketone species and you throw an alcohol or a water into it, many different things happen. So just talking about, I'll just point to things here, and then we'll talk about it more next time I see you. All right. So here, this alcohol here, this generic alcohol here, can just add in to your ketonic species right there, and kick up that pair of electrons right there. And after your proton transfer, you end up here with this thing called a hemiacetal or a hemiketal. A hemiacetal is when the R prime, or one of these R's here, is going to be a hydrogen, right? You'll have a hemiketal if this R prime here is an alkyl group, okay? So we're going to assume this R group here is going to be an R group, like a real alkyl group here. And a hemiacetal is only when the R prime or the other one is going to be a hydrogen, okay? And that's what we're going to say. Hemiacetal is going to be, hemi just means half, all right? And that's all that means. And so a hemiacetal versus a hemiketal. To be fair, to be honest, a lot of people don't even use ketal, this term ketal or hemiketal. Everything to them is going to be an acetal for some reason, but we'll do our best to use the real terms for the real exact things, okay? So normally these things are catalyzed by acids, okay? And if you take this guy here and you treat this guy here with another mole of alcohol, so you have 1 mole of alcohol here, this guy here attacks into that species right there, followed by a proton transfer, right, to give you this species here, because this hydrogen here is from this hydrogen right there. Then what you have here is another mole of this alcohol, or 2 moles of it here, come in and displace this guy here, right? And this guy here is displaced by a very specific mechanism. How do you think it goes from here to here, right? What do you think happens? Why don't you use your powers of deduction and figure out what you think happens here? I can give you a hint though. Notice how you have to use more acid here. Take some acid, throw it onto this guy over here, and make this species, right? Make the species right over here. And I'm assuming it's an oxygen. Ugh. OH2 positive, right? Make that species right there. So take this guy here, take this guy here. I don't know if you can see my cursor, so I'm just going to draw. Take your hydroxyl right there and protonate it, and make the species here. And once this guy here is protonated, right? What do you think happens after that? You've now made a good leaving group. Have this thing here leave. Explain to yourself. See if you could rationalize, which is explaining things to yourself. See if you can rationalize why this guy here would leave, and the fact that it leaves. Is there any stabilizing force behind it leaving? Is the remaining intermediate stabilized in some respect? And I think you find it will. Then once it's stabilized, attack it with another mole of this alcohol to get this overall species and see what you end up with. All right. So yeah, it's a short lecture today, but I just wanted to sort of catch up a little bit, and so we can finish this thing hopefully this week. All right. And also we have too many like way more important mechanisms to do that I don't want to scribble on the screen. So I'll do those on Wednesday and Friday for you guys. So I think we're good. Are we good? We're good. Any questions? Wow, none? Awesome. All right. Later on, folks.